extensively in the broad field of computation on encrypted computations, both in modeling and for constructions. So she has results concerning identity-based encryption, inner product functional encryption in general, in particular for uniform models of computations like Turing machines, also in obfuscation. And in her first talk today, she will tell us how to build lattice clusters.
Thanks, Damien, for the introduction. Thank you all for being here, and I'd like to thank the organizers for inviting me, and in particular for having this fantastic program and workshop. I'm really happy to be here. In fact, as I've been telling some friends, I think my main regret already is how quickly this program is going to end. So, it's really great to be here. All right, so I'm going to talk about lattice-based cryptography tools and applications. It's a very non-committing title. Let's think about what we want to do, right? So you've seen lots of lattices so far this week. Beautiful theory, some wonderful applications. We've also seen sort of the poster person application of lattices and in fact of all of cryptography, which is fully homomorphic encryption. It's my most favorite application. So you might wonder, well, what next? I mean, what's left to do? We know how to do old crypto. We know how to do fully homomorphic encryption. So what else is it that we'd like to do? So since, we're here, let's be ambitious and let's think about what's sort of one of the dream applications that we might have. So, if we could have whatever we wanted, then what's the kind of crypto we'd like to do? And a very good candidate for this dream application, at least in my mind, is the following example. So this comes from the field of personalized medicine. And here's a quote from an article that appeared in Nature a few years ago. This is what it says. The dream for tomorrow's medicine is to understand the links between DNA and disease and to tailor therapies accordingly. But scientists have a problem, which is how to keep genetic data and medical records secure while still enabling the massive cloud-based analysis that's needed to make meaningful associations, right? So now cryptography should somehow help here, and you might ask, well, doesn't FHE solve exactly this problem? And if you think about it for a minute, I mean, it doesn't really, not quite, right? Because for instance, if I'm a researcher who wants to do this, some study on encrypted DNA, I'd also like to figure out what's the result of my study, right? So once I run my experiments on this encrypted data, I'd like to know what this gave me. So FHE is not really letting me do that. And can we do that at all? Well, these are questions we'll start to address as we get deeper into this talk. Here's another example which I really like. So suppose I want to do access control, but on encrypted data, right? So here's a toy example. You have a professor who wants to encrypt some file so that other professors or admin assistants of the computer science group can open it. So now public key encryption gives you the following solution. Well, encrypt the file for each of the people that satisfy your criteria. But this is painful, right? I mean, this is not an elegant solution. It doesn't really match the requirements of what you want. Particularly, what if somebody quits, another new person joins, what are you going to do? Re-encrypt, and you'll have to keep doing this. So this is not a nice solution. And what you'd like really is to somehow encrypt your message against a formula, where the formula specifies your access control policy. In our case, this is our formula. And excuse me, you'd like this person to be able to encrypt this file against this formula somehow. And you'd like him to be able to, store it on some server and go away. There could be some trusted party in the system, let's call her a key authority, that hands out keys to different users depending on what attributes they satisfy. So, a professor, computer science, admin, these are all attributes that you might have associated with you, and you could imagine having keys that codify these attributes. And now, when you're in possession of these keys and, everybody tries to access this file, well, decryption should succeed if and only if your key possesses attributes that satisfies the policy against which the file was encrypted, right? So this is something that we'd also like, and this actually we can achieve. So we're going to see this today. So in order to sort of start moving towards these applications, we're going to need new tools and techniques. And the main new tool that I'm going to talk about is lattice trapdoors. Now this is something that we've already seen a little bit. So in Chris's talk, he already discussed this a little bit, but we'll see it in more detail. Okay, so before I tell you about lattice trapdoors, let's just review the definition of trapdoor functions. So you should be able to generate some function f along with some sort of secret information t, where the function, let's say, maps some domain D to some range R and is obviously one way, otherwise it's not even an interesting question. So here's my domain and range. I should be able to take a point x in the domain to its image f of x in the range easily. So this should be easy. Given f of x, it should be hard to go back to x, but given f of x and the secret trapdoor t, it should be easy to go back to x, right? So this is just the basic notion of a trapdoor function, and this is what we're going to hope to build. So obviously, since we're in this lattice program, our hard functions are going to come from, the hard lattice problems we've seen, the short integer solution problem and the learning with errors problem. So let's very quickly review the SIS problem. Here you're given a fat matrix A, right? These are the parameters for which it works. And the question is to find a low norm or a short vector x such that A times x is equal to 0 mod q. And as we've already discussed extensively in this workshop, if you don't have the requirement that the vector x needs to be short, this problem is trivial to solve. It's just linear algebra. But as soon as you impose this condition, this problem becomes really hard. I won't talk too much about the hardness of this problem. We've already seen that, right? So this is a hard problem. And of course, you have the learning with errors problem, which also we've seen in this workshop. The question here is to distinguish these noisy inner products from the uniform distribution. So on the left-hand side, I sample some vectors a1 up to am at random over some field zq to the n, and I sample I uniformly sample this vector s. I fix it for the whole experiment, and then I compute bi as ai inner product with s plus a little bit of noise, right? So this is on the left hand side, and on the right hand side the bi's are also chosen as uniform, and the question is to distinguish this, right? And we believe this problem is hard. This is the learning with errors problem. And all the work we're going to do in this talk is going to be based on the hardness of these two problems. So let's start defining our one-way functions and trapdoor functions, okay? So let's think of our public key as this matrix A. So again, this is a fat matrix, n by m. M needs to be at least n log q. Now based on SIS, I'm going to define my function f sub a in the following way. So f sub a of x is equal to just ax mod q. Okay, so you just compute the inner product, or the matrix vector product of a and x. And now here, of course, x has to be short, otherwise it's not an SIS instance. And since this matrix is fat, this function is compressing, right? So therefore, this function is going to be a surjective function. And Aitai showed that this function is actually a collision resistant hash function, assuming that SIS is hard. All right, and then based on LWE, you have a different function. This is an injective function. So G sub A of S comma E is S transpose A plus E transpose mod Q. Okay, so here this error vector is very short. It's shorter than the X in the SIS instance, and this function is injective. Regev and others showed, so Regev showed that this is a one-way function if LWE is hard, and there's been a lot of work subsequently on that. All right, so these are our two functions, and we're going to be interested in inverting them, as I already said, right? So in the first case, since the function is compressing, there are many pre-images to a given image. We're going to be interested in sampling from possible pre-images. Okay, so stated a little formally, excuse me. We're given some vector u, which is congruent to Ax mod q, and we're interested in sampling some vector x prime such that Ax prime is also congruent to u mod q. And in particular, we'd like to sample this x prime from among possible pre-images using a nice distribution. Okay, and in particular, the distribution is going to be the discrete Gaussian distribution, which we've seen already in this workshop. In the case of the LWE function, well, there's only a unique pre-image. So there the question will be just to find that pre-image, right? So we're going to focus more on the SIS based function, although we'll also see how to invert the LWE based function. So here, Gentry, Peckert and Vaikunthanathan defined this notion of a pre-image sampleable trapdoor function in order to support this kind of sampling from the pre-images. Okay, and what you want to be able to do here is really generate x comma y in two equivalent ways. So in the first experiment, you sample x using some distribution. It's going to be the discrete Gaussian distribution, and you compute y as f of x, right, Ax mod q. Or you have the other experiment where you first sample y from the uniform distribution, and then you use the trapdoor to sample x from the domain such that the relation holds. So in either of the two experiments, you get the same distribution for x and y, which is discrete Gaussian and uniform, right? But obviously the latter distribution needs trapdoors. Okay, so what do these trapdoors look like? So lattices are beautiful geometric objects, and some lattice cryptography also admits beautiful geometric interpretations. Not all of it, unfortunately, but in this case we're lucky. So what do these trapdoors look like? Let's try to see it geometrically. Okay, I'm going to talk first about the so-called type 1 trapdoors. We'll see later how these differ from other trapdoors, but for now, let's just look at this geometric view. Excuse me. So here's my lattice. There are two different bases here, and depending on which basis I choose, I can chop up the space around the lattice into these parallelopipeds, right? And for different bases, these parallelopipeds look different. So now here's a proof by picture. Okay, I want to claim that these bases are actually not equivalent to each other in every sense. So they're equivalent in the sense that they generate the same lattice, but there is some notion of quality that we can associate with this basis, and depending on which basis you have, some problems could be easier or harder. So again, in Chris's talk, he already talked about this a little bit, so I'm not going to go into detail. I'll just show you a quick illustration. Okay, so suppose I have a quite short and nearly orthogonal basis, then here's what I could do to solve the closest vector problem. Okay, so here I have this point t, which is an arbitrary point in space, and I'm interested in figuring out which is the closest lattice point. So using this good basis, I can output the center of the parallelopiped that contains this point, right? I mean, using any basis, I can output the center of the parallelopiped that contains the point. The question is how good of an answer this is. And if the basis is good, where I'm not going to define good formally, but if the basis is good, then this is a pretty good guess. But if the basis is bad, then this will be declared the closest lattice point, but you can see that there are closer candidates. So if the basis is bad, then what you get is not so useful. Okay, so broadly, I want to say that we've seen these problems, right? SVP, CVP, SIS, and in general, these are hard problems if I'm given an arbitrary basis of the lattice. But some of these hard lattice problems actually become easy if you're given a good basis. And as in cryptography, you're always looking for asymmetry, and this is the asymmetry that we're going to leverage here. by using this short basis as a cryptographic trapdoor. Okay. So at this point, let's say that we have this short basis, for some lattice. How are we going to invert the function that I talked about? So first of all, what is the lattice associated with this function? So you've already seen this. This is the dual lattice. So it consists of all points x such that Ax is congruent to 0 mod q. And if I have a short basis for this lattice, then actually I can sample from the pre-images using the right distribution. Okay, so this I'm just telling you as a fact. You should ask me, well, how do I do this sampling? But this is something that I'm not really going to talk about in this talk. So you can use the randomized nearest plane algorithm. The nearest plane algorithm is a classic algorithm by Babai. The randomized version appeared in GPV to the best of my knowledge. And Chris covered this in his talk, right? So he described how this algorithm works. So I'm not going to define it. So what I'm going to focus more on is the second question, which is that, fine, so if I have this short basis, I can use this randomized nearest plane algorithm, but how do I get this short basis, right? So this is what I'm going to talk about, almost, as you will see. So what do I mean by almost? I'm actually not going to talk about lattice trapdoors that are a short basis. I'm going to talk about something a little bit different, which are the so-called type 2 lattice trapdoors. This is not a short basis, but it's just as powerful. It's more efficient. It has better parameters, and it implies type 1 trapdoor. So it's better in every way, and these were constructed by Michiancho and Picard. This is what we'll focus our attention on. Any questions so far? Excuse me.
Is there some other type 3, type 4, or that's?
Not to the best of my knowledge, but you're the expert. So this type 1 and type 2 was defined in MP12, right?
But we didn't, I don't think we numbered them. I was just wondering if you had found more. And
No. Yeah, so this type 1, type 2 is also not my numbering. I think I've seen it in some talk by Chris possibly, although I may be wrong. But yeah, there's only type 1 and type 2, and actually they're very closely related, as we'll see. So, I still think of a lattice short basis as a trapdoor. We're going to see that you can make do with something a little bit less, but this type 2 trapdoor also sort of very, very immediately implies a short basis. So it's, almost the same thing, although sort of to be really precise, they're different, but it's almost the same thing. So I already showed you this. Okay, so let's look at these type 2 trapdoors. Okay, so here are the two functions that we want to invert, and how do we construct these trapdoors? So what we're going to do is the following. We're going to first start with a fixed gadget matrix G. So this gadget matrix has been showing up all over the place. It was also there in Vinod's talk. We'll see a definition of it in just a second. It's basically the powers of 2 matrix. Okay, so it's a fixed public matrix, everybody knows it. And we're going to say that, for this fixed matrix, let's first figure out how to invert these functions. Then we'll say that let's figure out a way to randomize this matrix into a fresh matrix, a nice matrix that I can use for my cryptographic constructions. And this randomization will be via a nice unimodular transformation. This unimodular transformation will actually be the trapdoor. And the third step is to reduce the inversion algorithms in the final randomized matrix to inversion algorithms in the fixed matrix. Okay, so this is the 3 steps that we're going to see. And as I already told you, it's the transformation in step 2 that will be our trapdoor. Okay, so let's go through each of these steps one by one. So let me first define G for you, right? As we already saw in Vinod's talk, this vector G is the powers of two vectors. So if I think of Q as 2 to the k for simplicity, I'm just going to define G as 1, 2, 4, in general 2 to the I up to 2 to the k minus 1. Now, the big matrix G is just going to be a bunch of parallel repetitions of the small g. So let's focus our attention on this vector G, all right? So now I'm interested in inverting LWE with respect to this matrix, this vector G. So I'm given some SG plus E, where G and E are vectors. I can just write this down in this way, right? So I just expand out the definition of G, and this is the vector that I get. Now you can see immediately how to invert LWE for this G, because consider 2 to the k minus 1 S plus some error. So since I've scaled S with 2 to the k minus 1, I've sort of really shifted S to the most significant bits, and then whatever error, I've shifted the least significant bit of S to the most significant bit, and now whatever error I add, as long as it's bounded, right, it's only going to mess up the coordinates in the least significant parts of the vector. I hope that's clear, right? So I'm just saying this is my vector, right? So this error is just going to mess up the coordinates here, right? So the least significant bit of S is going to be over here, and it's going to be untouched by this error. So I can recover that, right? And then I repeat this process, so I get it bit by bit, all right? So this will work as long as every error coordinate is bounded. Now, how do I invert the SIS function?
Quick question. So this works if Q is 2 to the k, but if Q is prime or something, then you use the same gadget matrix but do something slightly different.
Yeah. So I think you will have to worry about rounding error and so on, but yeah, I think that the same analysis should go through.
Yeah.
Yeah. So now I want to invert SIS, okay? So the algorithm is actually just the first line. I just worked it out for like a very simple example for concreteness, okay? So what do I want to do? Well, for I ranging from 0 to k minus 1, I'm going to sample some xi as 2z plus u. I'm going to sort of set u as u minus xi over 2, and then I'm just going to repeat. Okay, so just to make sense of this, I did like a very small example here which we can go over. So, that's if you want me to go over this example. Shall I, or is it? Okay, so some people are nodding. So let's just think of k as 2 for simplicity. So then what does this algorithm say? So for I starting with 0, I sample some 2z plus u. So let's say that I set x0 as 2z0 plus u, and then u is changed according to this rule. So you can quickly check that it works out to minus z0, right? And x1 will then be 2z1 minus z0, right? Now consider the inner product of g and x. So I'm just going to get 2z0 plus u plus 2 times x1, right? And that's just going to be u plus 4z1, which is u mod 4. So this is just, as I said, a very simple example which I just worked out for concreteness. So this is just how the whole algorithm works. It's very, very simple. Are there any questions?
So if you do deterministically exactly bit decomposition,
Yeah. So for inverting G, that's all you need, right? You don't need anything fancy. So this is really the sort of simplest first step. If we're not even looking at the matrix, we're just looking at the vector G, which is the powers of two vector, right? And we're observing that, if you're only interested in inverting LWE and SIS with respect to like this highly structured, vector G, you can just write it down. It's very, very simple. That's all. Okay? Yeah?
So this also, the inverting of SIS works only for Q power of 2, right? The smaller algorithm.
Yeah, so that's a good question. So yeah, I just worked it out for 2, powers of 2. It definitely works for Q of different arithmetic shape, but it will need a little more care. So I haven't worked it out in the slides. But it definitely works. Okay, so everyone's good with this? So for this highly specific G, these functions are easy. That's just the basic takeaway. Okay, so now, I want to mention, so this connection to the short basis, right, that I was telling you about. So I just want you to notice that, for this vector G, it's actually very easy for me to come up with like a short lattice basis. So for G perp, this is the basis, right? So you just write 2's down the diagonal and, minus 1's just below that. It's totally trivial to see that G times G transpose this is going to be 0, right? So this is a short basis. And I promised to tell you what the big G looks like, and as I also promised you, it's totally simple. So it's just a bunch of repetitions of G. You can write it formally as the identity matrix tensor this vector G. Okay, so this is going to be our fixed gadget matrix G, and inverting the SIS and LWE functions with respect to this matrix, it just reduces to parallel and offline calls to, the inverting the functions with respect to the small g. So, that's simple. Okay, fine. So now we know how to do step 1. So we fixed this matrix and we figured out how to do inversion using that. So now let's make things more interesting. Of course, I'm not interested in doing inversion for this fixed matrix. I'm interested in a random lattice with a trapdoor, right? So how do I get this random lattice? Well, I'm going to randomize G in a way that makes it look uniform. And how do I do that? So I'm going to first sample a uniform matrix B. I'm going to sample a short Gaussian matrix R of these dimensions, and I'm going to define A in the following way. So I'll concatenate B and G together, and I'll multiply them with this matrix. Okay, that's specified here. And what you get here is B concatenated with G minus BR. Now, why is this uniform? Or this is my matrix A, and I'm going to use this in all my cryptographic applications. I still haven't shown you how we get a trapdoor for it, but at least it should be easy enough to see that this matrix will look uniform. So B was already uniform to begin with. It was just chosen in this way. Here the G is fixed, there's no entropy there, but this R has a lot of entropy, right? So remember that this matrix B is again a fat matrix, and this matrix R is going to be, so let's think of R as being a square matrix. So let's think of M prime as being about n log q. So R is a square matrix in that case, and even if here I've said that it's Gaussian, discrete Gaussian, but even if it's not, even if it's just a binary matrix, right, it will follow from the leftover hash lemma that B times R is uniform. So for those of you who have not seen the leftover hash lemma, here's like a uber simplified version of it, which is just restating what I told you 1 second ago, that B times R looks uniform, and this is even given B. Okay, so as long as R has the right dimensions, which is to say as long as, think of it as a square matrix, as I said, even if it's binary, it has enough entropy to fully randomize B. Okay, so B comma BR is indistinguishable from B comma U. This is a highly specialized form of the leftover hash lemma. The original lemma is very, very general, but for our purposes we are just going to use this. Okay. So hence you get that this matrix A is uniform. Any questions? Alright, so then we have this matrix, and now I am going to define this type 2 trapdoor. Okay. So as I told you earlier, this transformation that we do to the gadget matrix, that is going to be our trapdoor. And to make it a little more formal, we say that R is a trapdoor for A with some tag H. So we can ignore this tag most of the time, but yeah, for completeness let's define it. R is a trapdoor if A times R stacked on top of I gives you H times G. So as I said, think of H as the identity to begin with. So this is basically saying that A times Ri is equal to G mod Q. Okay. And a short basis for G, which I already showed you, it was the 2's and the minus 1's, plus this R actually implies a short basis for lambda perp of A. And this is a pretty nice argument. Okay, so maybe I can show it to you very quickly.
So this is saying the type 2 trapdoor implies the type 1 trapdoor.
Yeah, exactly. Because you have the short basis for G, and I am telling you now that here's, this is what I defined as my type 2 trapdoor. So I am telling you that given this and this new trapdoor R, I can actually get a type 1 trapdoor. And this, as I told you, is fairly easy to see. So, or well, fairly nice to see, whether easy or not. So this is my matrix, right? So now I would like to sample some vector here so that I get 0 mod Q, right? That the product is 0 mod Q. So what can I do? Well, I am breaking it into these two parts. So on the top, really I have no leverage. So B is a completely uniform matrix. I have no clue what to do. So what am I going to do? I'll just sample a Gaussian vector. It has no connection to anything. It's just a vector, right? But now notice that. So and let me just call this as E2. So let me call them as E1 and E2. Okay. So now let's write it down. So we get BE1 plus GE2 minus BRE2, right? This is my left hand side. The nice thing is that I can cancel out this term here by writing minus RE2 on the top, right? So then I get BE1 minus BRE2 plus the rest of it as before. So this problematic term kind of goes away, and now the equation I need to satisfy is BE1 plus GE2 is congruent to 0 mod Q, right? So in other words, I need to, so E1 I sampled, as I said, without any constraints. So now I need to satisfy GE2 is congruent to minus BE1 mod Q. But this is something I can sample using the short basis for G, right? So I know that I can solve SIS or even the inhomogeneous version of SIS, the ISIS, it's a dangerous word, I'm on camera, but yeah. So I can use the trapdoor to sample E2 to satisfy this, and then I got a vector that's in the perp of this lattice A, right? The distribution actually is not quite right, but you can re-randomize. I'm not going to go into that. Okay, so here we have it. So type 2 trapdoor implies a type 1 trapdoor, and it's very natural. All right, so now the question is how do I reduce FA inverse and GA inverse to FG inverse and GG inverse, right? So we saw how to invert LWE and SIS with respect to G. The question is how to do it for A. Obviously, I need to use my trapdoor R. As I said, I'm just going to think of the tag H as the identity matrix for now. Later in applications, we'll need to instantiate it differently, but for now, just think of it as identity. So this is the, the equation that I have. So we're going to remember this equation, for the rest of this talk. So A times Ri is G. Maybe I'll also just write it here. Okay, mod Q. Cool. So this is our equation. Now I want to invert LWE. So that means I have, S transpose A plus E, and I want to figure out what's S and E. So here's what I can do. So if I just take this matrix here and I multiply it with B, then this is what I get, right? So B is SA plus E, right? So you can see, the S remains the same, and then I get A times Ri, which is G, right? So I get SG plus the error also times this matrix. But now, since this matrix R was chosen to be small, as I said, with Gaussian entries, you can bound the growth of this error. So this new error, as Vinod said, this is, a curse of lattice-based crypto. You don't know how to stop noise growth. You can control it, but you're always going to have it. So the noise will grow, but you can bound this. And in particular, we saw how to invert the function with respect to G. So now I've converted the function with respect to A to a function with respect to G. And now I can apply the method from before and invert it, right? This will work as long as the cumulative error is bounded, but I can take care of that. Any questions? All right, so now we're interested in inverting the SIS function. So to recall, I have U is AX mod Q, and I want to sample this X prime from the set of pre-images, right? And in particular, I want to do it using this nice distribution, or from this nice distribution. So here's a first attempt, okay? I know how to invert G. So let me invert U with respect to G. So in particular, that means I sample some vector Z from a nice distribution such that G times Z is congruent to U. Okay, so I did that. And now here's a first attempt, right? I can compute X as Ri times Z. So you can check that A times X is what? It's A Ri Z, but A Ri is G, so GZ is U, which is what you wanted. Is it clear? Yeah? So I managed to find a vector X which uses the trapdoor sampling with respect to G along with, the pre-image sampling with respect to G along with the new sort of trapdoor that I have. Using these two, I managed to find an X that satisfies the equation that I want. So this is progress. Are we done? And well, if I'm asking the question, the answer is no. So we're not done, because this vector X that I constructed here does not have the right distribution. Okay? So in particular, the covariance of X leaks R. So you can work out the covariance. It's about this, right? So it leaks the geometry of the basis. So R transpose is leaked by this, and this is a big problem, right? Because R is your trapdoor, and you can you can measure the covariance and you can get to R, and this is a big problem. So there are multiple ways of fixing this. Here's a nice way. You want to finally output a spherical Gaussian which does not leak the basis, right? So its covariance matrix should look like S squared times I. You can fix this using this nice perturbation method that was first suggested by Peikert, and it makes use of the following nice fact, okay? So if I convolve two Gaussians, the covariance matrices add up. So now let's look at what I want. I want to output this, right? I'm able to sample something that has covariance this. So what can I do? Well, I can sample another Gaussian which corrects for this covariance. So now these covariances will add up to give me exactly the right thing. So this is the hope. How do I implement it? Well, I'll generate this perturbation vector with the right covariance, but now I sample z, the original vector that I sampled with respect to z, with respect to g, I'll sample that differently. So instead of gz equals u, I'll sample it as gz equals u minus ap, right? And what I'll output is p plus riz instead of just riz, right? So this is sort of, it's really very natural. We had riz, it had a problematic covariance. You smudge the covariance, but then the image changes. So you sort of also change z to account for that. So it's very natural.
Sorry if it was already mentioned, but is it clear that when we sample using this G, that we get a spherical distribution? You invert using
Yeah, that's a good question. I don't think I explained that explicitly.
The question was when you
No, I think it's easier if she repeats her part.
Yeah, so he was asking that he notes that I did not really talk about the distribution of the pre-image of like when I sample with respect to G, right? So I showed how to do it. So if I
just wanted to hear the question again. With anyway, it's fine. Okay, just
no, I'm telling you the question. Maybe there's a cleaner way of saying it, but this is the equation, and I showed how to sample z to satisfy this equation given a u, right? And he's asking whether it's clear that that's a spherical Gaussian.
That's the guarantee.
It is the guarantee, but I didn't talk about it. That's all, yeah. I didn't prove it in the talk, but yeah, that's the guarantee. Yeah, so I mean the answer to your question is that I didn't answer it, but it's true. Okay. Okay, yeah, so as I was saying, this is a fairly natural method. You sort of fix the covariance and then you adjust for the difference. And you can sort of check very quickly, right? So ARI is G. Now A times X is AP plus ARIZ, which is AP plus GZ, which is U as desired. Okay, and now we have the right distribution that we wanted. So the takeaway for applications is the following. Here's how I construct a random matrix A, right? So I sample this B. I sample B is uniform, I sample R as a Gaussian, and then I just compute G minus BR and I concatenate the two. This gives me a random matrix by the leftover hash lemma. Using the trapdoor for G and this type 2 trapdoor R, I showed you how to invert the LWA and SIS function with respect to A. So this is sort of the generation of the lattice along with the trapdoor, right? So now we can use this for applications. So we can talk about applications. I want to ask the organizer or chair whether I can go into, or I should go into applications now, or should I just start that in the next talk?
15-20 minutes. Does it fit? Do you have like a section that fits in 15-20 minutes?
I could just define something. Yeah.
So is there a reason why type 1 or type 2, how do they compare to each other? Like why should we?
Which ones? The two trapdoors? Yeah, so the type 2 trapdoors are more efficient. Yeah, so they are better.
So we don't know how to go from a type 2 trapdoor for a matrix to a type 1. No, the other way around.
That's what I did here.
The other way around, we don't know, right? They're not equivalent in the sense that.
Let me think about it. Well, I guess, yeah, so this type 2 trapdoor really, it needs a very specific algebraic structure. So if I have some matrix A and I write it as A1, A2, you're asking the question of whether I can write this as A1 G minus A1 R. This is the question you're asking, right? Yeah, so I would imagine that using a type 1 trapdoor also you can do this, right?
Type 1 trapdoor for A1, for sure. But if you have a type 1 trapdoor for A, it's not clear that you can.
Yeah, that's indeed true.
Probably it's false. It's probably
Yeah, that's true. So since I have a trapdoor sort of for the whole matrix A, it's not clear that I could write A2 as G minus A1R. If I had a trapdoor just for A1, then I could do that. That's a good point. Yeah. Any more questions? All right, so that's all I wanted to say about trapdoors. Now we'll talk about applications of these trapdoors. Okay, so the main applications that I'd like to show you are related to functional encryption. I'm going to define some specializations of functional encryption, and I'll show you how to construct them. So the first one that I'll start with is identity based encryption. Now this is a very nice primitive. It was first defined by Rivest and just Rivest? Shamir, sorry. Just Shamir? Okay, yeah. So Shamir posed this question I think in 1978 or something.
Okay. 84.
84, okay. I wasn't around. So yeah, so what's identity based encryption? It's public key encryption in which any arbitrary string can be your public key. Okay, and the sort of the motivation that we give for this primitive coming from the practical point of view is to avoid scams of certificate authorities and so on. But it's really mathematically a very natural primitive. Here's how it would work. So you have these users Alice and Bob. Now Bob would like his public key to just be his email address. Okay, so how should this work? Alice should just be able to encrypt her message using Bob's email address, and she sends it to him. Now he needs to have a secret key that corresponds to this public key. So how does he get the secret key? Well, there's a key authority that he can go and authenticate himself to. And if he convinces the authority that this email address belongs to him, he'll get back a key using which he can decrypt this message. And the way that I've presented it, she sends him the email first or the message first, and then he gets the key. But he doesn't have to do this every time he needs to decrypt a message. So it's just a one-time operation. You contact the key authority, you get the key, and now anybody can send you any number of encrypted messages, and you can decrypt them using that. Okay, so a little bit formally, this is what the scheme should look like. These are the algorithms that we want to construct. So there's a setup algorithm. It's going to take the security parameter. It will output some public parameters or public key and a master secret key. Okay, so this master secret key is really sort of a it's like all the security in the system sort of lies, is held by its strong shoulders. It's really, so this master secret key can be used to decrypt anything in the system. So it's sort of quite problematic in that sense. But for the moment, we are going to live with it. So this master secret key, along with any arbitrary string, some identity, ID, can be used by the key generation or the extract algorithm to get a private key corresponding to that string, right? The encryption is public key, so this is pretty standard. So you take the public key, you encrypt the message, but now you also encrypt it with respect to some identity, right? So the public key is the identity of the person that you want to read the message, and put together, decryption will work if the two identities match up. Yeah, so it's clear. So the key has an identity built into it, the ciphertext has an identity built into it. If the two identities match up, then the key decrypts and recovers the message for you. So this is the definition of the primitive. And maybe since I have a few minutes, I'll just recap the public key encryption scheme of Regev. We've already seen this a few times. Vinod also talked about it, and also others before him. But for completeness, I'll also define it. And then we'll see how to modify this encryption scheme to get identity-based encryption and even more powerful generalizations. So this is the scheme. We're going to look at sort of the dual version of the scheme that Vinod showed. Okay, so what do I mean? Well, you'll see. So I'm going to start with my SIS equation. So A times E is U mod Q, and I'm going to make E secret and A and U to be public. I'm just defining a public key encryption scheme. That's all. Okay, and this is the relation that holds. Now, in order to encrypt some message, what do? Well, I pick some random vector S and I compute these two LWE samples with respect to A and U, and I add my message to the second ciphertext component. Okay, so to be completely precise, I should have like a scaling factor here, because in the end I'm going to recover some message plus noise, and I should be able to separate the message and the noise. But for the purpose of this talk, I'm just going to ignore this error correction. Okay, so this is my ciphertext. How do I decrypt? Well, it's very natural. So, I take my secret key E and I compute E transpose C0, right? Sorry. E transpose C0 is going to give me U transpose S plus E transpose noise. Again, I can bound the noise, and then I subtract C1 from it. This gives me message plus more noise. Okay, so again, I want to mention that in my talk, this term noise is used as a placeholder. So, E times noise is still noise. I'm not going to keep track of how the noise gets modified. The only invariant that we need to assume is that the noise is always bounded. So you have some modulus Q, and whatever accumulation of noise you do, you should sort of remain below some threshold, like Q by 4, let's say. All right, and I can scale the message by Q by 2, and this will let me disambiguate. So this is the encryption scheme. This version of Regev's encryption scheme, which first appeared in GPV, as far as I'm aware, is something that's used in all the systems that we'll see for the rest of the talk or for the next talk, right? So we really want to sort of keep track of this scheme. And I'm going to introduce some notation that will make life simpler. So this matrix A here, I'm going to refer to it as the encryption matrix, okay? And what we're going to see is that when I want to do identity-based encryption, or more generally attribute-based encryption, essentially we keep the same structure of the scheme. What we change is this matrix A. So for identity-based encryption, for instance, I told you that now the public key is a random or arbitrary string, right? So in order for me to encrypt with respect to an arbitrary string, I'm going to somehow change this encryption matrix A into a different matrix that encodes that string. And I'm just going to do the same thing, exactly the same thing. So this A will change into some other matrix. The key generator will, sample this E with respect to that new matrix, and the rest of it will be just the same. And this is actually true for all the schemes that we'll see, and in fact for most schemes in this family. And here, of course, I don't need to say this again. So the cumulative noise is only going to be small if the vector E, the secret key, was low norm to begin with. Only then can I bound the noise. Okay, so the broad structure of the IBE, as I already told you, is that I want to embed this vector ID in the ciphertext and the secret key. So I'm going to sort of change this encryption matrix. I'm going to now call it some FID, and this will somehow encode the ID. We can encode it in different ways, as we'll see in the next talk. This will be publicly computable, and it will be a function of ID and the public parameters, and we're just going to perform, regef public key encryption with respect to this. That's just all we're going to do. We'll figure out a way to compute a short vector E such that this equation holds, right? And basically that will be, this will be the structure of all the schemes that we'll see. And in fact, most of the schemes that exist, like I'll have to think of, I can think of a counter example, but for the most part, the schemes look like this. So I think this is a good place to stop. So we've seen sort of the broad structure of identity-based encryption schemes, and when we come back after lunch, I'll show you how to build them in a couple of different ways. Thank you.
Other questions?
Yeah.
A question back to the pre-image sampling from Chapter in general. So you described like we know how to sample from discrete Gaussian distribution. So it's still an open problem to sample from, for example, uniform distribution with as
with bounded norm.
as possible. Like
I don't know. So Daniele may know.
Sorry, I just cannot hear it. So can you repeat the question?
The question is that instead of Gaussian, can you do sampling from the uniform distribution, like for the pre-image?
yes. So yes, there's an answer from like a rejection sampling. Is that the only one you are thinking about?
So one solution
I
is
haven't seen it actually.
Doesn't seem efficient. I mean, sure, you can just use generic techniques like
Yes.
rejection sampling, but it doesn't seem that would be efficient.
I mean, I have a polytime solution. It's not going to be as tight. It's not going to be as short as Gaussians.
So you're thinking like it's not gonna be. Does that mean like you have a proof like how to say like is it just the limitation of the current technique or?
I don't know. Yeah.
It's not as good as Gaussians.
So do it.
But why do you want to? Because you think it will be more efficient, or it will have better applications? Efficiency. Yeah, I definitely don't know of a efficient way to do it. Yeah, there may be a way to do it, but it's probably not helping, because if it's not even more efficient, then what's the point? Right.
We have one trick, right? Gaussians.
That's what I'm saying, yeah. No, I mean there are papers that look at replacing Gaussians with uniform from small, like uniform in a bounded space, but I don't, in this context, I'm not aware that it would help you.
There is also a problem with, so is the Gaussian matrix this G?
Yes.
So if you do uniform sampling and then you apply the transformation R,
Yeah.
like uniform in a cube, then that's going to reveal information about the secret key, which is something you want to hide.
You want to end up in the cube at the end.
Oh, you want to end up in, okay.
Yeah. You want to do the convolution trick, whatever that means here.
Yeah, I mean the distribution is something you might be able to take care of, but
Oh wait, Leo is claiming that he can do it. That's
A lot of people can do it.
And you mean like
It's not particularly new or particularly clever. I think there's even a paper of Vadim about
Vadim, yeah. So
the
that's,
rejection sampling, right? Yeah.
No.
This is like the Pierre
Vadim and Daniel Bix. Is it the one you're thinking of?
Yes.
I don't know.
I'm not an expert on that paper, so I'm not going to commit to this.
That's what I remember.
So my question is, can we do better, right?
Yeah, my answer is I don't know of a way. That's my answer. Maybe there is a way, I haven't seen it. Yeah. Any other questions? Lunch. Yes.
The gadget G itself. So are there other potential gadgets? Is it like an optimal gadget? Or is it
Yeah, that's a good question also. So, again, I don't know of a better way to do it.
So this is about G, the gadget G. No, yeah. So there is so some of these generalizations, and so this is something that is explored in a number of papers. So I have a paper in Eurocrypt 18 and one in Eurocrypt 19. One of them is doing arbitrary modulus, which for pre-image sampling is a bit tricky, requires some additional work, and I think Eurocrypt 19 is where we consider, for example, CRT gadgets rather than power of 2. And
I see. I wasn't aware of that. Okay.
it comes up, for example, if you want to implement things in the RNS form, you can get more efficient. So in practice, yes, it can be convenient. So these CRT type of gadgets, I think, were used first in a paper of Shai, Halevi, I think.
For what?
Others, using gadgets that involve Chinese remainder theorem structure. So that's something that I think first appeared in some of the papers about RNS implementation of the system. So it is often considered more of an implementation issue than cryptographic design issue, but yeah, you can design specialized algorithms for other types of gadgets.